S. Chand presents educational video lectures as per the new UGC CBCS curriculum. Absolutely free. Difficult science concepts made easy. Study anywhere, anytime.
Hello everyone. Can you tell me what is the common feature between these two molecules over here? One is DDT and the other is hexachlorophene. Look at them carefully and see if you can identify the common feature. I am Dr. Sujata Sengupta. Welcome to the S. Chand Academy. If you want to learn more about today's lesson, then please refer to the book by S. Chand Publishing, the link to which is provided in the drop box below. Taking a look at these two molecules more closely, one, remember, is DDT. DDT is dichloro diphenyl trichloroethane, and the other one is our hexachlorophene. DDT, if you remember, was a famous synthetic pesticide which was widely used, but until recently its use has been banned due to its toxic effects. Our hexachlorophene is also an example of a bactericide, and it was very commonly used in many of our cosmetic products. But recently it too has also been banned because of its toxic effects. But let's forget that. What is the common feature between these two molecules? If you have guessed correctly that they contain a halogen atom, more specifically, if they both contain chlorine atoms bonded directly to an aromatic ring, you are absolutely right. Both these molecules are examples of aryl halides, and both of them can be synthesized from chlorobenzene. So in today's video, we are going to learn all about the chemistry of our aryl halides. The chemistry of our aryl halides is quite distinct from that of our alkyl halides. They do not typically undergo nucleophilic substitution reactions by an SN1 or SN2 mechanism. I hope you have been watching our videos regularly. If not, do go back and refer to our videos on alkyl halides and their chemistry, which is posted in the S. Chand Academy. So what are these aryl halides? So an aryl halide is an organic compound where a halogen atom is bonded to a carbon present in an aromatic ring. The aryl halides are also known as halobenzene. For example, chlorobenzene, bromobenzene or iodobenzene. How do we name these aryl halides? Well, the common method is we add the prefix fluoro, chloro, bromo or iodo to the name of the benzene framework, and we will use a number to locate its position. Since our aryl halides are also aromatic compounds, so the nomenclature rules typical to that of our aromatic compounds will also be followed. So we can use the terminology of ortho, meta and para. And as always, different substituents are going to be named in an alphabetical order. In terms of the physical properties, our aryl halides are similar to that of alkyl halides. They're also polar molecules. Why? Because it contains the carbon-halogen bond. Since they are polar molecules, so their boiling points, their melting points and the solubilities will be similar to that of alkyl halides, which will contain the same number of carbon atoms. Now, let's come to the synthesis or the preparation of these aryl halides. How are they made? The two most common methods for the preparation of our aryl halides is either from benzene, the halogenation of benzene, or via the diazonium salt reactions, which is also known as the Sandmeyer reaction. Let's look at our halogenation of benzene. So the halogenation of benzene is one of the most common and the traditional methods for the synthesis of our aryl halides. Here, the reaction, it follows an electrophilic aromatic substitution mechanism, and generally catalysts like aluminum trichloride or FeBr3 are commonly used for these reactions. The other common method for the preparation of the aryl halides is known as our Sandmeyer reaction. During the Sandmeyer reaction, a diazonium salt reacts with our cuprous salts. How do we prepare diazonium salts? I hope you remember that when aniline is treated with nitrous acid at cold temperatures, we are able to synthesize our diazonium salts. What are some of the reactions common to our aryl halides? Well, one of the most important reactions is the formation of our Grignard's reagent. Remember, Grignard's reagents are an example of our organometallic reagents. That is, with the general formula RMgX, where the magnesium, the metal, is bonded to our carbon atom. Grignard's reagents, how are they prepared? Yes, remember, they are prepared by treating our alkyl halide with magnesium metal in the presence of anhydrous ether as the solvent. And why are Grignard's reagent so important? Because they serve as a very important reagent, which is a source. They are nucleophilic, and so they can attack electrophilic carbons in different molecules. Similar to alkyl halides, aryl halides also react to form our Grignard's reagent. In addition to Grignard's reagent, aryl halides also react to form organolithium reagents. In the beginning of our lesson, what did I say? That these aryl halides do not show the typical SN1 and SN2 nucleophilic substitution reactions, which were characteristic of the alkyl halides. Why is that? We can look at its structure. Number one, the steric hindrance that is caused due to this benzene ring, it prevents an SN2 attack. Furthermore, our phenyl cations, we know they are unstable, so it cannot be formed if we have an SN1 mechanism. And finally, the carbon halogen bonds in our aryl halides, they are shorter and they are therefore much stronger. It is not easy to break these bonds. So, does that mean that a nucleophilic substitution is not going to take place on aryl halides? No, it can take place, but under certain conditions. This low reactivity of the aryl halides, it can be changed. One, if we take aryl halides which contain strong electron withdrawing groups attached to it, for example, if it contains nitro groups in the ring, or when we use strongly basic nucleophilic reagents. So let's look at this in more details. Nucleophiles, they can displace the halide ion of our aryl halides, particularly if there is a strong electron withdrawing group present in the benzene ring. Because the nucleophile is going to substitute a leaving group or your halide ion on the benzene ring, so therefore it is a nucleophilic substitution reaction and it is given a name of SNAR, substitution nucleophilic aromatic. As I've mentioned, the presence of strong electron withdrawing groups on the benzene ring favors this type of a nucleophilic aromatic substitution. How does this reaction proceed? It proceeds by what is known as an addition-elimination mechanism. So, let's consider the nucleophilic substitution reaction, for example, of 2,4-dinitro-chlorobenzene in sodium hydroxide solution. So, here I have my 2,4-dinitro-chlorobenzene in the presence of sodium hydroxide. It's a nucleophilic substitution reaction. So let's look at how this mechanism proceeds. Here I have called it my addition-elimination method. So what happens? In the first step, step 1, it will involve the attack of the nucleophile onto this benzene ring. Here you notice that my benzene ring has the presence of two nitro groups, strongly electron withdrawing groups. So they pull the electrons away from the benzene. I also have a chlorine atom, which is also by nature is electron withdrawing. So in my first step, I will have my nucleophile, which is the hydroxide ion. This is going to come and attack the carbon on the benzene ring attached to the chlorine. What do I get? I will get an intermediate with the following structure. Alright, so attack by the nucleophile, my hydroxide, onto the benzene ring gives me my negatively charged sigma complex, which, if you noticed, will be stabilized through resonance. I'm not drawing the resonating structures, I'm sure you can draw it on your own. In the second step, what happens that there is going to be the loss of the leaving group. Which is the leaving group? Yes, it's the chlorine, which is lost as the halide ion. So here I will now have the loss of my leaving group, my Cl minus, and what do I get? I will get my 2,4-dinitrophenol. But remember, the reaction is not going to stop here. Why? Because phenols are acidic and we have a basic medium. So this phenolic proton in this basic medium is going to get deprotonated. And what does that give me? That is going to give my phenoxide anion. This phenoxide ion in the final step is going to get protonated either in the presence of water or if we treat it with dilute acids, and we end up getting our desired product, which is our 2,4-dinitrophenol. So this is a nucleophilic substitution reaction on the aromatic ring, but it involves what we call as an addition-elimination mechanism. Before we take a break, let's see if you can solve this reaction over here. Here I have the reaction of bromobenzene with a very strong base potassium amide taking place at low temperature. It is a nucleophilic substitution reaction on the benzene ring, but can you tell me, will this proceed by the same addition-elimination mechanism as we have discussed?
हाय, मैं हूं नेहा शर्मा और मैं आ रही हूं एस चांद अकेडमी में आपके फिजिकल केमिस्ट्री के डिफ़िकल्ट कॉन्सेप्ट्स को इजी बनाने। सो प्लीज़ हमारे चैनल को सब्सक्राइब करिए ताकि आप अपनी सारी फिजिकल केमिस्ट्री की प्रॉब्लम्स को भूल जाएं और सबके सॉल्यूशंस आपको मिल जाएं।
Welcome back to the S. Chand Academy. Before we went for our quick break, I had left you with the question of a reaction of the low temperature reaction between bromobenzene with potassium amide. It's also an example of a nucleophilic substitution reaction on the aromatic ring. If you remember that the addition-elimination mechanism which we discussed earlier, it works best when the benzene ring contains the presence of strong electron withdrawing groups, for example, the nitro groups. It is possible to have a aromatic nucleophilic substitution reactions on aryl halides that do not have this strong electron withdrawing group. Sometimes what's required is a very harsh condition. So, for example, under high temperature and high pressure, chlorobenzene is converted to the sodium phenoxide when reacted with sodium hydroxide. But let's come back to the question which I had asked you. Here we have the low temperature reaction of bromobenzene with a very strong base potassium or sodium amide at low temperature. Here the reaction, you will notice, it proceeds by what is known as an elimination addition mechanism. So, how does that happen? Let's look at the mechanism. The following steps is going to highlight how the elimination addition mechanism operates. In the first step, our very strong base sodium amide, it abstracts a proton from the carbon which is alpha to the carbon bearing the halogen atom. And when it does so, it leads to the formation of a carbanion. You will notice here that in this carbanion, the negative charge, it lies on an sp2 hybridized orbital. In the next step, what happens is that this carbanion will expel the bromine in the form of a Br-. Alright, what do we end up getting? We end up getting a reactive intermediate which is commonly termed as a benzyne. it is written as this benzene ring with the presence of a triple bond. These benzyne reactive intermediates, they are extremely unstable and highly reactive. And so in the third step, our strong nucleophile, our amide, can come and attack this benzyne at either of the carbon atoms. And it reforms our carb anion, new carb anion. This will then abstract a proton from the ammonia, our solvent, and it gives our product aniline. So, this mechanism, which happens through the benzyne reactive intermediate, is known as the elimination addition mechanism. So, in summary, this benzyne mechanism will operate when the halobenzene is unactivated towards nucleophilic aromatic substitution, and when the forcing conditions are going to be used. It's a two-step elimination addition mechanism which occurs through our benzyne intermediate. Finally, our aryl halides will also show reactions which are typical of the aromatic nature of the benzene ring. In other words, they too will also undergo electrophilic aromatic substitution. But here, there are two things that we need to remember. Our aryl halides, which contain the halogen atom bonded to the aromatic ring, they will show reduced reactivity in terms of electrophilic aromatic substitution. Why? Yes, because the halogens, by virtue of its inductive nature, pulls the electrons in the benzene ring away towards itself. Therefore, they will inductively remove the electron density from the benzene ring. As a result, the electron density in the aromatic ring, it decreases and it deactivates the ring. So, the halogen atoms will make the aromatic ring less reactive towards the upcoming electrophile, and that is why they are regarded as deactivating groups. So, chlorobenzene is going to be less reactive than benzene towards electrophilic substitution. However, when halobenzenes do undergo electrophilic substitution reactions, they react predominantly at the ortho and para positions. That is, they are ortho-para directors. Why? That is due to the resonance effect. That is, it is due to the presence of the non-bonding electrons present in the halogen atom. So, let's take a look. So, in chlorobenzene, these non-bonding electrons will be involved into the aromaticity of the ring. We can draw resonating structures. Keep moving our electrons to draw the resonating structures. And now, what do you notice? So now what do you notice? That it is the ortho and the para positions which are least deactivated in terms of electrophilic aromatic substitution. So I hope you have enjoyed today's video. We looked in details in the chemistry of these aryl halides. More specifically, we looked into our nucleophilic aromatic substitution reactions. Keep watching our videos where we will also be discussing the chemistry of phenols, another important class of aromatic compounds. Please do like, share and subscribe our channel, and don't forget to hit the bell button. Thank you.